So I've got a lot of thank yous here. The guys at Southern Cross Uni, our own technical staff, Sunshine Sugar, in particular the sugarcane farmers who had all been extremely generous with their time in helping us set up the field sites and maintaining the field sites. Jeff, Alan, Rob and Wayne, Marguerite of course, the staff from SRA, Diane Allen and Daniel Cozzolino, and also more recently I'd like to acknowledge Kirsten Verberg from CSIRO. I think a lot of our data is going to be applicable to some of the modelling approaches that Kirsten is starting to work on, so there'll be more coming out of that in the near term. Like a lot of the other projects, really what we're after is to get improved nitrogen use efficiency and productivity. In this case, it's in the sugarcane industry. And I guess coming into the project, and this was on the grand scheme of things, a fairly small project, but what we are trying to better understand is what are the stocks of nitrogen in the soil in New South Wales prior to sowing, and are current fertiliser recommendations adequate in those particular systems. The other aspect really is better understanding controlled release fertilisers. In this case we were using polymer coated urea to better match nitrogen sugar cane demand with supply. And I think most of us understand here that it's really that supply curve that's very important for optimising nitrogen use efficiency. Why have lots of nitrogen up front when the plant doesn't need it? You need it when the plant's growing at its optimal. So really the aim of then these slow release fertilisers is to better synchronise supply and demand. So the research questions were, what are the stocks of plant available N? What soil properties influence these nitrogen stocks? And does polymer coated urea do what it is actually meant to do? So we'll discuss that a bit later in the talk. And during the project itself, we had a couple of additional research questions that popped up just from some of the data that we were getting. And I guess the main one being, we all understand mineralisable nitrogen, and we all kind of know how to test for that, being a 14-day test or a 56-day test or whatever it might be. But the problem with that particular test is, it might be too late for farmers to act on it. So, farmers need potentially a test that can predict mineralisable nitrogen more rapidly for fertiliser decisions. By the time they get the data back, too late. Too late to get on the field. And the other thing too is I had a lot of, I won't say the term whinging, but a lot of comments back from the technical staff who are out in the field, sampling sugarcane that might be 2 metres high in 35-degree temperatures and 100% humidity and brown snakes, and they're going, surely there's a better way to have a look at crop nitrogen uptake in sugarcane, and I guess that's why we are starting to employ some of the UAV technologies, including the green DVI index for having a look at nitrogen uptake, and I think there's some really promising outcomes out of that. Rightio, enough of what we were proposing, this is what we did. Okay, so we had a look at 41. So previously I'd reported on 27 sites, we've now updated that to 41 sites, having a look at a range of soil properties and mineral N from the field. These involve taking cores to 1 metre, pooling them, etc. We all know the gig. This is some of the data. So we split our field data up into 3 catchments. So you've got the Tweed River catchment, which is right on the border with Queensland. Interestingly, a lot of the soils there are hydrosols or peat-based soils, and across on the right-hand side you can have a look at the carbon content. They tend to have quite high carbon contents because they are peat-derived soils. We typically might see 5, 6, 7, 8% carbon in the topsoil. But what we also noticed in the Tweed catchment is that all of these soils are also very, very acidic, and that's an important piece of data in some of the following slides. As we've moved further south, so the next catchment down is a Richmond catchment, so that's sort of around the Ballina area, and it tends to be a lighter texture than the Tweed River, a little bit lower organic carbon, but the organic carbon's still not too bad, 2, 3, 4%, but our pH tends to be a little bit more neutral. Still a bit of acidification in the topsoil, but certainly down at depth it's pretty reasonable. And again, we go a bit further south down to the Clarence, you sort of think Grafton for that region. Again, slightly lighter textured soils again, slightly lower carbon content, and the pH is not looking too bad at those particular sites. Had a look at root distribution. What's quite interesting is in the Tweed River, we were actually finding roots down to a metre depth, even though they're quite acidic. Yet on some of these lighter textured soils, like in the Cairns River, the roots tend to be confined to the top sort of 60 centimetres of soil. And that's an important point to note when we're having a look at existing nitrogen stocks in your soil. If your roots aren't getting to them, what's the point in having a nitrogen stock measurement at 1 metre if the roots can't get there? So there's obviously some other constraint limiting root growth, and I think Gunnar and Graham talked about some other constraints that limit root uptake of the nutrients and also water. So here are some of our results. So in that top bar, it's a bit of a stacked column graph here. The red relates to the Clarence, green the Richmond, and blue the Tweed catchments. And along the x-axis, which is the important one, we're just having a look at the nitrogen content. So what we can see from this is that the Tweed sites tended to have a little bit more ammonium than the other sites, and they tended to have a lot less nitrate in them. Interestingly, so the mineralisable nitrogen data that I've presented here is a 14-day, stock standard 14-day PMN test. We had up to 250 units of PMN, 14-day PMN here, and it ranged from pretty well nothing up to 250 units. We added all of those together, and some of these sites had existing nitrogen stocks of between 150 to 400 units of nitrogen. So one might ask, if you are a cane grower and you've got 400 units of nitrogen in your soil, do I actually even need to add nitrogen fertiliser in that particular case? The other point to notice too there is that the 14-day PMN test grossly underestimates what might be available across the season. So our 300-day PMN ranged from 140 through to 560 units of nitrogen being released as nitrate into the soil across that time range. Now, also that's relevant for sugarcane because in New South Wales it's often grown over a 2-year period. Often in that second year, it's very hard to get further nitrogen into the ground. So having a nitrogen supply from the soil that extends beyond the first 90 days is actually quite important. And clearly, I think in these systems, the potentially mineralisable nitrogen coming mainly from the breakdown of new and old organic matter is, I think, quite important for the crop nutrition. It would be nice to better quantify what the relative contribution from new organic matter, i.e. that's the detritus and the leaf and trash, versus the priming effect, so the breakdown of soil organic matter. And there's actually, I was meant to present a poster on that, but we've got a paper on the priming effect of sugarcane trash on soil organic matter degradation, and it's quite significant. It's an important contributor to nitrogen supply. Okay, going back to some of these very acidic glasols and also hydrosols. What's quite interesting in these soils, there's a paper that a colleague of mine, Terry Rose, did I think last year. It got published. So we were having a look at these glasols and impact of liming on these glasols. And top left you can see the ammonium content over time, and the ammonium stays as ammonium. We add lime to those soils and that ammonium turns to nitrate. So that's pretty well, it's not an astounding piece of information. We kind of know that nitrification tends to be inhibited below, I don't know, is it 5.2, 5.3 pH in calcium chloride? But certainly it does provide an option now for management of some of these soils. So for example, the sugarcane soils and the hydrosols don't have a lot of aluminium. They can handle the low pH, but maybe in those soils we don't lime them. Maybe we just use the natural low pH as a nitrification inhibitor. It's a very effective nitrification inhibitor. Okay, now we're going to move on to the polymer-coated ureas and the enhanced efficiency fertilisers. I've shown this slide before, again another paper from Terry Rose at Southern Cross Uni. One of the issues that we found looking at the literature on enhanced efficiency nitrogen fertilisers is a lot of the studies have been done focusing on nitrous oxide emissions, and as such they would often then compare your stock standard urea application with your urea plus an inhibitor, for example. The problem with that is it doesn't necessarily relate to yield because the crop's already at this optimum end dose. It's more about the data is more focused on the gas emissions. But we did find 11 studies in that use suboptimal nitrogen doses, and what we have shown there in that meta-analysis is that the inhibitors can certainly, and this is from global data, the inhibitors can certainly result in improved crop yield when applied at suboptimal doses. So rather than applying your stock standard nitrogen recommendation, if you're applying it at 50 or 75 or 25%, you definitely get improved yield over the standard urea. So what this has told us, and certainly the recommendation out of that paper, is that it's actually quite critical to get a nitrogen response curve. Doing, I think, single point reductions in fertiliser application with the EEFs doesn't necessarily tell you the whole picture of what's going on. So do these polymer-coated ureas do what they're meant to do? So again, this is that nitrogen supply and nitrogen demand topic that I mentioned before. So we buried the polymer-coated urea in bags, nylon bags, in our special control plots, and we came and collected them at certain periods of time, and we had a look at how much nitrogen was left in them. And lo and behold, they actually did pretty much what we thought they were going to do and what the fertiliser manufacturers told us they were going to do. So we've got two polymer-coated ureas, the thinner coated PCU 90 and the heavier PCU 270. So the red line is basically just, so the y-axis is just nitrogen remaining in the fertiliser beads, and the x-axis is time. And you can see here that you've got a decay curve of nitrogen from the polymer-coated urea. It does exactly what it's meant to do. And we calculated a release rate 50, however you want to term that. We did that at two different sites. This other one was at Woodford Island. Again, I need to stress that both of these sites had well below average rainfall years. This curve might change to some extent had that rainfall been higher. We don't know. So the key result is the T50% release from the 90-day polymer was about 30 days, and from the 270-day polymer was about 90 days. Most of the polymers had a little bit of residual end even after about 200 days. So they did, I think, what the manufacturers were telling us they'd do. So testing these in the field, and I'd just like to point out that doing these field trials was quite challenging because they're polymer-coated urea. It's actually quite slippery, and it took a lot of effort for the tech staff to calibrate the equipment for accurate dosing in the field, and that's just our design. You can have a look at that in more detail in our final report, which Margarita's got online somewhere. Okay, our first site was at the Tweed catchment, and in the middle of the picture there is the Cat Challenger that we used for harvesting all of our field sites. And that's the same bit of kit that they use for the variety trials in New South Wales, and it's got a weigh bin accuracy, I think, of 10 or 15 kilos. So it's a fairly accurate piece of kit that we used for harvesting the field sites and collecting yield data. Okay, a little bit of a messy graph, but what we can see here is an end response curve where we applied 0, 50, 100, 200, 300, 400 units of nitrogen, the green dots being the nil, the orange dots being the orange polymer, and the blue dots being the standard urea fertiliser. And what's really interesting there is we've got a fairly flat end response curve, and we couldn't separate out the differences between the polymer or urea. Now, to me, that's telling me that, in particular, so even the nil fertiliser still had quite a good yield. That's probably telling me that the soil is supplying a fair bit of nitrogen. And we kind of know that from our studies from the Tweed Valley that the soils are supplying a fair bit of nitrogen. What was interesting, though, is that the nitrogen uptake did actually increase with increasing N doses. So the leaf N content, or the total N content of the biomass, increased over with increasing nitrogen fertiliser rates. Have a look at the second field trial. Maybe a little bit more nitrogen responsive. We got maybe not quite double the yield, but close to double the yield with the highest rate of N applied. Again, we're a little bit disappointed that we couldn't separate out any effects on yield between the polymer coat and the standard fertiliser. And I need to stress again, and I'm going to probably do that 3 more times in the talk, that these were drought years. And our N loss pathways, our potential losses, from either leaching, or probably more likely denitrification in some of these systems, just wasn't there. You're not going to get these N-loss pathways. So potentially in these particular years, there's no particular need for these enhanced efficiency fertilisers. Okay, third field site, Clarence catchment down near on basically Woodford Island near Grafton. Again, not a huge nitrogen response with increasing nitrogen supply. Fair bit of variability in the field. We had 3 reps, and it was difficult again to separate out any effects of the polymer versus standard urea. What we did find though is that the polymer did actually end up with slightly more nitrogen in the leaf material. So we do actually get increased nitrogen uptake by the crop with the polymer, and certainly increasing the nitrogen dose results in more leaf nitrogen content. That doesn't necessarily translate to increased yield of sugarcane though. This is where we did some of our testing of UAV technology, and we put a whole heap of different spectra at it. The standard NDVI, GNDVI, and a few other indices. And what we found is at 160 days, we actually had a really tight correlation between the green DVI or GNDVI with leaf nitrogen content. And that kind of held pretty well through to when the crop starts to dry out a little bit. So I think certainly for our field trial purposes, where we're having a look at nitrogen uptake in the crop, we can use some of this information going forward to do the work more cheaply. Again, going out in the field, taking leaf samples, getting them analysed is timely and expensive. This is cheap and fast and pretty damn good too. And at our 4th field site, lo and behold, again, disappointing result. No separation of the PCU from the standard fertiliser with yield. But again, we were getting a little bit more uptake of nitrogen into the leaf material with the polymer coat. So I could show a whole heap of different ways that we've sort of calculated fertiliser use efficiency. I like the method that Mike Bell has proposed, looking at agronomic efficiency of the fertiliser. Certainly at Stotts Creek, you can see there that we had an agronomic efficiency of 18% at low fertiliser dose, and as you increase fertiliser dose, I think a couple of speakers have already mentioned that, I think Graham in particular, you start to lower your agronomic fertiliser use efficiency. It's not rocket science, we kind of know that. At Pimlico, we had a really nice nitrogen response there as far as agronomic efficiency goes. Woodford Island and Corokai really had no response to fertiliser at all at those particular sites. Some of the key results. We had generally flat nitrogen response curves from 4 sugarcane trial sites to increasing nitrogen dose. That could be a couple of reasons. One being that these sites actually do have a fair amount of pre-existing nitrogen stocks in soil, be it mineral N or mineralisable N. And part B, probably the years that these field sites were run, we were limited by water. Water limits crop growth limits nitrogen uptake, and therefore nitrogen becomes far less important. Had this been done in an above average rainfall year, I am sure that the results would be different. So the polymer coated urea definitely resulted in higher uptake of nitrogen, but that didn't necessarily translate to higher yield. And what we did also find was that polymer coated urea did result in higher residual nitrate content at harvest. So that now starts to impact the following season's crops, which I think could be a good outcome for the industry. And GNDVI provides a good proxy for leaf nitrogen content. So just really quickly, the other thing that we have done is using mid-infrared and also near-infrared assessment for potentially mineralisable nitrogen in a couple of the catchments. And this really cheap, really fast test appears to be quite accurate actually in giving us a bit of a proxy for 1456 and also 300-day PMN. So rather than having to wait 300 days to get your data back, we can tell you overnight what your predicted PMN is going to be in that particular soil. And I think there could be some opportunities here for the sugarcane industry and possibly other industries as well to take this type of information further forward. I need to stress that this is all about calibration, and our calibration is really tight for our 3 catchment soils, which tend to be quite constrained. This is not going to work for Graham's vertisol or Peter's chromosol or whoever, other soil types. So there are some definite constraints there. Industry outcomes. Polymer coated urea did not influence yield across the 4 trial sites. But as I mentioned before, there were constraints, in particular availability of water. The mid-infrared provides a useful prediction for mineralisable nitrogen, and I think we could actually start looking at that as a commercial test going forward for growers. And also multispectral imaging is useful for predicting leaf nitrogen content. Right, so some of the stuff that we'd like to do with our data, and as I mentioned, I've already had some preliminary discussions with Kirsten Verberg, is certainly the release rate from the polymer coat in the field is new data, and it's quite important, and she'll be able to use that in some of the models where we understand crop end supply and end demand, and overlaying some of the climate information or the predicted rainfall data in different seasons, I think will be quite important. So we did actually approach SRA on this a little while back, but it's something I'm going to pursue. I think we've got some nice data that can be used, I think, for more practical outcomes for the industry. I would also like to acknowledge Wayne Rogers, who was tragically killed last year in a farm accident on his property, tractor accident. Incredibly generous man. Thank you.